should be working now. Thank you.
Okay, all right, let's talk about LT Spice. So I'm going to assume that you've already downloaded LT Spice. You already have used it a little bit. You kind of get, you know sort of the lay of the land just barely, and you want to learn more about how you can use it for bigger and better things, and also to be just proficient at it, so that instead of just being something that you're being forced to learn, it's something that's actually a tool that you can pull out whenever you need it, whenever you need to solve a problem. Okay, so what we're going to cover, we're going to talk about basic simulation types, .op for operating point, .dc for DC transfer, .ac for AC simulation, .tran for transient, and .noise for noise simulation. We're going to talk about the role of simulation within design flow. We're going to talk about parameter stepping, stepping parameters, and temperature, and viewing waveforms and so forth. We're going to discuss troubleshooting, and we're going to talk about some resources for further learning. Okay, so let's talk about some basic examples just to grease the groove of using LT Spice for basic purposes. So this is a pretty standard .op simulation. This is a linear circuit, meaning that all of the components in this circuit are linear. Let's go ahead and try to draw this circuit. Can I? No, I can't pull this over to the side. All right, let's take LT Spice, and I'll put LT Spice to the side here. Okay, we can do that. All right, so we'll just start a new schematic, Control N, and we'll add components. For your hotkeys, if you're using the default hotkeys, add component, I believe, is F2. I've rewired it so my hotkeys are different, so I press A. So I'm going to add a component, press A. The first component I'm going to add is going to be a current source. So in here, I'm going to start typing current. And you can see that the search bar found a current source. I'm going to hit OK. Now when I move my mouse around on the schematic, I'm going to specify where on the schematic this current source is going to exist. Firstly, I want it to point up, so I'm going to rotate it twice. Hit Control R to rotate it 90 degrees, and Control R again to rotate it another 90 degrees. All right, we'll just click on the schematic to place it. And then it wants us to place more. If I just keep clicking, I'll just keep adding more. If I want to escape out of that, then I can either hit the escape key or right click. So I right click there, and I'm just going to delete all of these extra ones. F5 is the hotkey, although I've rewired my hotkey to X. So there's X for my hotkey. And to delete one component, you click on it. To delete multiple components, you drag a box around all of the components that you wish to delete. Okay, right click to escape from that. Okay, next component we're going to add is a voltage source. So let's do the add dialog again, F2. You could always use the bars up here. Where'd it go? This one for component. But I never do that. It's just too time consuming. I like hotkeys much better. So again, use the hotkey. I have A for my hotkey. And start typing in voltage. And there's a voltage source. We'll click OK. Add the voltage source to the schematic. Okay, the other types of components we need are resistors and a ground. So I'm going to hit R. That brings up a resistor. Type Control R. Well, actually, let's see. This first resistor is not rotated. So let me just click it once. Then type Control R to rotate. I'll add a second resistor. Click. We'll rotate it again to make R3. Control R to rotate. And then rotate again for resistor 4. I'm kind of shoved over here on the schematic a bit, and that's kind of inconvenient. I want to move to the right a bit. If I drag my mouse to the right, it kind of moves me along the schematic. Another approach that you can do is you can use your scroll wheel to zoom in and out. So if I just zoom out and then move my mouse over where I want to zoom in, and then scroll to zoom in there, then that's also a way that I can reposition the schematic on my screen. So I'm going to click again. Okay, and then right click to stop adding components. You'll notice that things are not quite arranged the way that I want them to be yet. That's fine. And let's add a ground. So type G to add a ground, and we'll just click on the schematic. Okay, right click. Now I'm going to move components around. There are two types of movement there's the open hand move and there's the closed hand move. Open hand move is called move, closed hand move is called drag. Drag is the one that I almost always use. The open hand one I hardly ever use. Sometimes I use it, but hardly ever. So most of the time I use drag. The hotkey for drag, I believe, is F8, although for me, I changed it to M. So I'm just gonna type the hotkey and then drag a box around the components that I want to move around. Okay, and I'll move this around there. If I want to rotate a component, I can do that too. Okay, so I can rotate these again, doesn't really matter. Okay, and then I'll start adding wires. So F3 for draw wire, I've changed my hotkey to W. So W for draw wire, or in your case, F3 most likely, and then just start clicking around to draw your wires. One thing you'll notice is that when you draw a wire through a component, instead of shorting out the component, it automatically cuts the wire. That's kind of nice. It helps you draw schematics more quickly. I'm just going to drag this ground over to make it look a little bit neater. And I'll drag this current source over to make it look a little bit neater. Watch this, by the way. So drag, again, is the closed hand move, and I use a hotkey M for it. If you just click on a component, then the component itself moves around, and the connections remain there, but the wires start getting all bent out of shape. If you want to drag those wires with it so that it maintains that nice square shape, then you drag a box. You enter the move mode, or you enter the drag mode, and you drag a box around all of the components and all of the wires that you want to drag. Okay. All right, so we've got our schematic looking nice. Let's start adding the values of our components. This is a 1 milliamp current source, so I'll just right click on the current source. It says DC value, 1M for 1 milliamp. R1 is a 1K resistor, so I'll type 1K. So again, it's right click on the component to edit its value. All of these resistors are 1K resistors, so I right click on the component, or I can right click on its value. You'll notice it has two pieces of text right next to it. One of them is the name of the component, R4. The other one just says R. The one that just says R, that's its value. So I'll set its value to 1K. I can either click the component to set its value, or I can click on the text that is its value. Either one of those works. Remember that if you right click on the name of the component, that's a totally different thing. That's not the value. I could give it another name, right, if I want, but that's not going to change its value. Okay, the last component that we need to add a value for is V1. So I'll right click on it and give it a DC value of 5 for 5 volts. Okay. And then the last thing that we need is a simulation type. So we can see on the schematic that we're copying a .up simulation. So in order to add a simulation, I'm going to hit the key S, and that brings up this text box to add a SPICE directive to the schematic. And the SPICE directive that I'm going to add is a .up, .op. Now this SPICE directive is attached to my mouse, so I'm just going to have to click on the schematic somewhere to place that SPICE directive. And now it is a full, complete schematic that has all of the components and a specification for what simulation is going to be run. Now I can simply run the simulation. I can hit the running man, or I set up my own hotkey, which is the tilde character. Either way, run the simulation, and now what do we get? We get all of the node voltages of the circuit. So how many nodes do we have? We have a ground node, 0. We have, so that's 1 node, 2 node, 3 node, 4 nodes, right? We have 4 nodes, but one of those nodes is ground, so we know its potential. We know that we don't need to solve for it. So that means we have 3 unknown nodes, and that's what is being reflected here. We have 3 nodes. The simulator automatically, or LT-SPICE automatically gave each one of these nodes a random name. Node 1, node 2, node 3. And these are the voltages associated with those nodes. And it calculated all of the currents associated with the branches connected between those nodes. So whatever branches connect nodes are components, a current source, a resistor, a voltage source. So it's showing the current in that current source, the current through those 4 resistors, and the current through the voltage source. Okay, cool. So that's pretty boring. Let's move on to the next circuit. But first, before we do that, let's have a look at a little detail. If I click on View and then click SPICE Netlist, it brings up this dialog, which shows, watch this, I1 0 N001 1M. What is that? That is a specification for a 1 milliamp current source that's connected between node 0, which is ground, and node 001, and its value is 1 milliamp. Likewise, there's a voltage source V1 connected with its positive terminal at node 3 and its negative terminal at ground, and its value is 5. And then this is resistor R1. It's connected between node 001 and ground, and its value is 1K, and so forth. So this net list is representing all of the nodes and all of the branches within this circuit. Anytime that you draw a schematic and then simulate it, that schematic is converted into this net list before it is then sent to a parser, which generates a matrix. The net list is parsed to generate a matrix equation, and also to generate element stamps within that matrix. And then that matrix equation is then solved using Gaussian elimination and back substitution, which is exactly what's happening when we run the .op simulation. Okay, so all of that is pretty similar to what you've learned in your circuit analysis course, except it's all being done automatically. Technically, the technique is called modified nodal analysis. It's similar to nodal analysis, but with a slight modification. You can look into it at your leisure. I'm not going to go into it. Okay, so is everybody tracking so far?
Yep. So good.
Cool. All right, let's move on. So we can also perform a .op simulation with a circuit that has reactive elements. So I'm just going to open a new schematic, and we'll add a voltage source. I'm going to follow the same procedure. Add a resistor, add an inductor, L for inductor, Control R for rotate, C for capacitor. Okay, I'll add a ground, G for ground. Start drawing wires. I'm just going to draw the wires straight through all the components. Okay, so there's our circuit, and let's start right-clicking and adding values. This is a 2-volt voltage source. This is a 1K resistor. This is a 1 millihenry inductor. Come on. This is a 1 nanofarad capacitor. And we'll run a .op simulation. So S for spice command, and then .op for the simulation type. And we'll click to add it to the schematic. And then we'll just go ahead and hit the running man, or I have a hotkey for it. So we'll run the simulation. And same kind of dialog appears, okay? It says the voltage at node 001. So again, we haven't specified which node is what, but the voltage at node 001 is 2 volts. Voltage at node 002 is 2 volts. Voltage at node 003 is 2 volts, which is kind of expected, right? The only nodes in the circuit that are not ground are attached to either the voltage source or this node, and we're finding basically the DC value of the voltage. Right, this is a low-pass filter, and the DC value of all of these voltages is going to be whatever voltage that this voltage source has. Okay, so basically in .op simulations, because we are trying to find the DC operating point of all of the node voltages and all of the branch currents, it just takes all of these reactive components and treats them as their DC values. Namely, a capacitor is treated as an open circuit, and an inductor is treated as a short circuit. Okay. Now watch this. If I hover my mouse over a node and look down at the bottom left where the status bar of the window is, it says this is node 001. And it says the DC operating point of this node is 2 volts. So that's basically what was reflected in that pop-up dialog that appeared, except that I don't have to read it out from that text. Right? If I put my mouse over this component V1, it tells me what the current through this branch is. It says 0.054 femtoamps, so 50 attamps, which is basically 0 to a good degree of precision. Also, if I double-click on a node, then it brings up this nice, cute little label that labels what the voltage of that node is. Say, for example, I change the voltage of this voltage source by right-clicking on it and setting it to 1 volt. Now, before anything updates, I have to rerun the simulation. So let's rerun it. Okay. Now it says everything is 1 volt. If I close this dialog, it shows these DC operating points of all of these nodes. Okay, let's move on. So let's talk about a nonlinear circuit, or a circuit that has nonlinear components. So let's add a new schematic. Let's add a voltage source. We'll add a couple of resistors. Okay, we'll add a diode, D for diode. And then we'll bring up the add component dialog for an NPN transistor. So I'll just type in NPN. If you're ever curious what else is in there, you don't have to type into this. You could just start browsing around and you know, looking through all of the components to see what's available. But since we know that an NPN is available, we can just search for it or click it. Okay, right click. Let's change this resistor to a 1K resistor. I can also copy this resistor. I believe the hotkey for copy is F6. I use a key V for it instead. So I just copy it and then click somewhere else in the schematic to show where it's being copied to. We'll add a ground, and then we'll just start drawing wires. So I'll draw a wire here, here, there. Just drag it through all these components, drag it through these, and then we'll add a base connection for this NPN. Okay. Now, let's give this voltage source a value, 10 volts. Now, the tricky thing about diodes and NPNs is that the simulator doesn't know what the value of it is. And unlike a resistor or a capacitor or an inductor, a diode or an NPN or a MOSFET or something, it doesn't just have a single value. It has what's called a model, basically something that describes more than one parameter. For example, an NPN transistor might have a beta. It might have an early voltage. It might have a transit time, right? There's a bunch of different parameters associated with that NPN. So it would be a little bit weird to just right click it and give it a single value. So instead what we do is when we right click it, this dialog shows pick new transistor. And when we click that, we can pick one among a bunch of different transistor models. For transistors that are available on the market, like the 2N2222, 2N3904, and a bunch of other NPNs that are available on the market. And if you look to the right, it shows you what the SPICE model looks like. It says dot model 2N2222 NPN, saturation current of 10 femtoamps, early voltage of 100 volts, forward beta of 200, and so on and so forth. All of these different parameters associated with this model. So I'm just going to select the 2N2222. It's a very popular NPN transistor that you can find for about 5 cents on the market. And for the diode, we're going to pick a 1N4148. So I'm just going to right click on that diode, click pick new diode, and select 1N4148. Also a very popular and cheap common diode. Okay, now we're going to add a SPICE command. So I'll hit S and type .op to run an operating point simulation. So same simulation we've run just before. And if we hit the running man, we get the same kind of dialogue. Okay, so node 001 is 10 volts, so that's obviously this node. We have node 003 at about 0.7 volts, node 002 at also about 0.7 volts, and the various device currents. One thing you'll notice is that unlike the diode and the resistor and the voltage source, which have just a single current, because the device, the diode or the resistor, simply spans across 2 nodes. It branches across only 2 nodes, and therefore whatever current that flows between those 2 nodes flows through that device, or rather whatever current that flows through that device between those 2 nodes doesn't involve any other nodes. Okay. In contrast, the NPN connects to 3 different nodes, so therefore we have to break out the 3 different terminals and specify the current associated with each one of those terminals separately. Now, one thing you'll notice is that some of these currents are positive and some of these currents are negative. That's because, as conventionally defined, when you have a multi-terminal device like an NPN, all of the currents that you read, that it tells you, are currents that enter that terminal. Okay, so let's just do some of those tricks that we just did before. I can hover over this and double click it. I can hover over this node and double click that. I can start dragging stuff around to make it look a little bit neater, I suppose. Okay. All right. So how does this stuff work? So we mentioned previously that that LT-SPICE uses modified nodal analysis, and that it generates a matrix equation that represents the circuit, populates that matrix with element stamps, and then uses Gaussian elimination in order to solve that matrix. It uses Gaussian elimination in the forward direction, and then uses back substitution. Now, on top of that, this simulator also has an iterative numerical solver. Something very similar to those of you who've taken microelectronics and you encountered transcendental equations. You have to, there's a very large, in fact, most equations that exist in the world are not analytically solvable and can only be solved using iterative numerical techniques. Approaches similar to how you solved resistor diode equations in your microelectronics course. There exists a set. In general, there are infinite ways that you could potentially approach an iterative problem. But some of the more common ways include Newton solving and the secant method, and a collection of other techniques. Now, there is no single numerical solver method that works for all types of nonlinear equations. And so therefore, the simulator is kind of tweaked by whoever wrote the simulator to handle well the types of equations that are typically encountered in electronic circuits. Okay, so how it works is that the matrix equation is populated with element stamps, and the element stamps for the nonlinear components are linearized about an assumed operating point. And then what linearized really means is that there is a version of that component's characteristics that is representative of the first derivative. In a large matrix, that's often called taking the Jacobian of the matrix. But really what it means is we're taking not just the device currents, but their derivatives. And their derivatives are important because that you need their derivatives in order to use the Newton method or the secant method or a bunch of other different types of numerical solving techniques, of iterative solving techniques. Okay, so once a numerical solving technique is employed, and if it is beginning to converge upon some sort of a solution, and convergence is not guaranteed, right? Convergence depends upon certain circumstances. So often the simulator will try one numerical solution technique, and if it doesn't converge, then it will try a different numerical solution technique out of a collection of different techniques. But eventually, hopefully, it finds a technique that is that does converge for the given circuit. And when it, as it converges, a metric is used, a set of metrics actually, is used to determine when has the circuit been solved to satisfactory accuracy. And that is determined by basically tolerances. So the simulator has a set of tolerances. In fact, you can see those tolerances if you hit the toolbar, if you hit the control panel and look at SPICE. You look at the right-hand side here, these are a bunch of tolerances. Gmin, abs-tol, which is a current tolerance, rel-tol, relative tolerance, charge-tol for how many picocoulombs or how many femtocoulombs, tr-tol, voltage-tol, and so forth. These are all tolerances that the simulator uses to determine when it is satisfied, when it has satisfactorily reached a close enough solution. And generally speaking, those values are pretty tight. So whatever numbers that you read out from your simulation are substantially more accurate than what you could expect from a circuit that you build. Because when you build a circuit, the deviation between one manufactured diode to the next is going to be substantially larger than the tolerances, than the numerical tolerances that your simulator is using. So it's not really that big of a deal, the fact that you don't arrive at an analytically correct answer to within zero error. Okay, the error is usually small enough. And usually LT-SPICE finds a decent way to converge on that answer. Okay, all right. So let's move on. Let's talk about DC simulations. So I'm just going to start a new simulation here, or start a new schematic. I'll add a voltage source, and I'll add a second one, and I'll add an NPN. And let's add a resistor, R for resistor, add another one. Okay, let's add a ground, or just add a bunch of grounds, I guess. Okay, start drawing some wires. Okay, we'll right click on this one. We'll just call it 0 volts. We'll right click on this one. This is our power supply, if you will, 10 volts. So we'll think of V1 as being sort of like a signal source and V2 as being like what powers this circuit. For R1, I'm going to set it to a 1K resistor. For R2, I'm going to set it to a 3K resistor, because why not? As for this transistor, if I right click it and click pick new transistor, the dialog shows me only transistors that are available on the market. Let's say, for example, that I wanted to pick a transistor that's not on the market. Maybe I wanted to provide a model for a transistor of my own, because, I don't know, let's say that you're working on a manufacturing process to create new transistors, and you want to be able to model that. You want to be able to do some math. You've done some math assuming a certain saturation current and a certain beta, and you want to confirm your math, right? So we can do that. If instead of right-clicking on the transistor itself, if instead I right-click on this is the model that it's using. I right-click on it, and instead of NPN, I type in my NPN. Now, currently, there's no model for my NPN. Okay, so let's say, for example, I type .op and run a simulation. It should complain, can't find definition of model my NPN. Okay, there's no model. Why? Because I didn't give it one. Okay, so let's create a model for that transistor. Hit S to add a spice command, and I'll start just typing out a model. .model, that's a spice command to create a model. The name of this model is going to be my NPN. And what type of device is this? It's an NPN. And the parameters of this NPN are a saturation current of, say, 1 femtoamp and a beta of 100. Okay? So there's my NPN. I'm just going to delete this .op statement. So again, for delete, that's F5. It's really, really handy to know your hotkeys. I suggest that you, as much as possible, go away from using these buttons at the top and move to hotkeys, because it's just so much faster.
Question
Okay.
about hotkeys.
Yeah.
Where do you go to reset those?
To reset the hotkeys,
Yes.
you hit the toolbar, and where it says drafting options, press hotkeys.
Oh, excellent. Okay, thank you.
All of those. Okay. And I'll have a table at the end of this. I'll put out my slideshow so you can see what my hotkeys are. I optimized my hotkeys so that I could have my left hand on the keyboard in a very limited location and my right hand on the mouse. Okay. All right, so there's my model, and I'm going to run a DC simulation. Now, because there's no simulation command on the schematic at the moment, if I hit the running man, it automatically brings up this edit simulation command window. And it gives me these options: transient, AC analysis, DC sweep, noise, .dc operating point. That's what we just did earlier, right? You'll see .op. And what we're going to do is a DC sweep. So it's a .dc command. What source do we want to sweep? The name of this voltage source is going to be V1. Oops, V1. Why V1? Because that's the default name that it came with when I put it on the schematic. Type of sweep, linear, why not? Start value, let's go from 0 volts to 10 volts. Increment, I usually skip the increment. You can specify an increment so that it forces, so that LT-Spice will specifically find points along a certain grid. But I usually skip it because I don't like to think about it. Okay. Oh boy, what just happened? All of my other open schematics got retiled with this. So I'm just going to minimize all those, and I'm going to hit the retile button again. One thing I'll mention is that when it comes to tiling windows, if you hit Control Panel, where it says Operation, I believe, yes, there's this default window tile pattern. You can set it to horizontal or vertical. On a wide screen like mine, vertical is usually what's best. because on a widescreen, you want your schematic and your waveforms to be side by side. So I leave it on vertical. It's not the default, but that's what I like best. Okay. So it brought up this secondary window, which is a waveform viewer window. And currently it's not showing anything because I haven't selected anything. If I put my mouse over anything now, you'll notice that it turns into weird stuff. If I put the mouse over a node, it brings up this little voltage probe cursor, which indicates that if I click it, then it shows the voltage of that node. Okay. If I hover over a component and it brings up this, it looks kind of like an owl, but it's actually a current probe. So it's showing the current flowing through the component in that direction. If I then click on the component, then it shows the current. It brings up the current on the waveform window. Let me go ahead and retile this in the other direction because my screen's kind of eaten up at the moment. Okay, so let's just look at what we're kind of interested in. This is the voltage that's being swept. If I click on something twice, then it gets rid of all of the other waveforms. So check this out. I can like start populating a bunch of different waveforms, and now I'm like really confused about what is what. I can begin deleting. Here's something that you'll notice. Whenever I have the schematic selected, you'll notice that it looks like this little mini window is focused. All of the various menus and stuff are associated with a schematic editing. If I click on the waveform viewer, then these menu items change. Okay, and so now they are representative of what tools are necessary to change the waveforms. So I could begin deleting waveforms. So here's the cut tool, which is F5, or in my case, it's X. And I can begin deleting waveforms and just start all that stuff, or right-click to get out of it. Or I can go back to my schematic and just click on a node twice. And then it just only plots that one waveform. Okay, so this is the voltage. This is the node attached to the voltage source that we are sweeping from 0 volts to 10 volts. And guess what? That node's voltage goes from 0 volts to 10 volts. What's on the x-axis is the parameter that's being swept. So if I right-click it, you can see that the quantity plotted is the voltage of voltage source V1, okay? And it's going from 0 volts to 10 volts, okay? You can also change the quantity that's being plotted. You can just type something else like VN01 or something like that, but I'm gonna skip that. Okay, so what's on the x-axis is what's being swept. What's on the y-axis is whatever you clicked. So I clicked this node, and so the voltage of node 003 went from 0 volts to 10 volts as the value of V1 went from 0 volts to 10 volts. No surprises there. Okay, how about this? This looks kind of like an emitter degenerated common emitter amplifier, right? So the output of this amplifier is going to be this node right here. So if I click it, you can see that it does indeed come down the way that an inverting amplifier would, and its slope is about 3. And then at some point, it begins to rise because the diode from the base to collector turns on. The BJT enters saturation. But until that point, between when it's in cutoff and when it's in saturation, in between here, it's in the active mode and it behaves like an amplifier with a gain of about 3. How do I know that the gain is about 3? Well, I could use cursors. I could like click on it. If I click on the name of a waveform, it brings up a cursor that I can then drag. I can drag this cursor around. If I click on the name of the waveform a second time, then it brings up a second cursor. So here I've got these two cursors labeled 1 and 2, and I can put this little dialog at the bottom shows the horizontal position of cursor 1 and the horizontal position of cursor 2, as well as their vertical positions and their differences, okay? So actually it doesn't really matter which, I mean, I could put this at 1 volt, let's say, and then put the second cursor at 2 volts, and then I could do the math, right? A 1 volt delta on X and a 3 volt delta on Y. 3 divided by 1 is 3. a -3. Or it automatically does that math for us at the bottom. You can see that the horizontal difference between these two cursors is 0.977 volts. The vertical difference between these two cursors is 2.8 volts. And the slope, which is the gain, is -2.86. Okay, so that's nice. We can use that stuff. Another neat trick that you can do, let me show you something. I'm going to right-click in the waveform viewer, and I'm going to click Add Plot Pane. Okay, let me just drag this around a little bit. Okay, now in this new plot pane, I'm going to, you can select plot panes by the way, by clicking which plot pane you're currently selected. So I'm going to click this plot pane that I've just added, and in it, I'm going to right-click Add Trace. And we could just add a trace that's already existing. For example, if I click voltage at node 003, I'm just getting the same plot that I have down below. But another thing that I can do is I can just type something totally different. So in order to change the expression, in order to change what you're plotting, you could just right-click. Left-click brings up the cursors, right? But right-click brings up this dialog, which allows you to just type whatever you want. So here I'm going to type the voltage at node 002, which is the green one that we've already plotted down below. And I'm going to plot something different this time. I'm going to plot D of. So D is a built-in function within LT-Spice that allows me to take the derivative. If I plot the derivative of a voltage with respect to the input voltage, then I get the gain. Okay. So within this regime here, which is the regime that we care about, let me just drop a cursor on it. Within this regime, the gain appears to be about -2.9. It varies a little bit depending on what exactly the operating point is, 2.875 and so forth. As the transconductance of the BJT gets higher, it gets closer to a gain of -3. And then it enters saturation and the gain becomes approximately 1. Okay, cool. Neat little tricks that we can do. So how do DC simulations work? Well, the simulator actually performs a .op simulation first. Basically, you see this .dc command. We're sweeping the voltage V1 from 0 volts to 10 volts. So it starts off with V1 being 0 volts. It starts with this value being 0 volts, and then it performs a .op simulation to solve all the voltages and all of the currents in the circuit. Once it's solved that, then it plots that first point. Then it steps that voltage source just a tiny bit, and all of those voltages and all of those currents are used that it found from the previous simulation are used as a starting point to begin the iterative solver for the next point. And that process is repeated. So that way it's leveraging the difficult work that it did when it performed that first operating point analysis to find all of the rest of those operating points. All of the rest of them come much faster than the very initial one. Okay, cool. Let's minimize these. So let's bring back, which simulation is it? This one maybe? Yes. Okay, so we're going to change this one. Instead of just running a .op simulation, we're going to run an AC simulation. So I'm going to right-click on the .op, and instead of DC operating point, I'm going to click AC analysis. So type of sweep, we can choose octave, decade, linear list. I normally pick decade, which means it's a logarithmic sweep. And I'll usually put in, say, 100 points per decade. Okay, so it's going to simulate the AC response at 100 different frequencies for every decade of frequency that it sweeps over. The start frequency, we're going to pick at 10 hertz, and the stop frequency, say, 10 megahertz. So we're going to sweep over 6 decades, right? 10 to the 6. And each one of those decades is going to have 100 points. Okay, and this is the command that is associated with that. We'll hit OK. So now that's the simulation. Let me just move that over to make it look cleaner. Now there's something else that we need to do in order to run an AC simulation. Let's watch what happens. If I just hit the running man right now, no AC stimulus found. This is an error. We have to set the value of a current or voltage source to AC1. It doesn't have to be AC1, it could be AC something else, but 1 is usually what's most convenient. Okay, so let's go ahead. We have only one voltage source here. I'm going to right-click on this voltage source, and I have to click this button that says Advanced in order to change it into an AC voltage source. So I'll click Advanced, And where it says small signal AC analysis, .ac, I'm going to click AC amplitude, and I'll type in 1. 1 what? 1 volt. So it has a DC value and it has an AC value. I'll hit OK, and you can see that it has both of these values specified. Let's hit the running man. Oh, did it run? Okay, it did run. Okay, so what exactly happened? When you run an AC simulation, the very first thing that it does is it uses whatever DC parameters exist, such as this 1 volt for this voltage source. It uses all of these DC parameters. It treats the inductor as a short circuit, the capacitor as an open circuit. It solves the dot-op simulation first. And then it uses that dot-op simulation to find all of the DC operating points, all of the conductances and admittances and impedances and so forth of all of the components in the circuit. And then it simply performs a linear analysis. It creates a matrix wherein all of the reactances of all of the components, all of the impedances of all of the components are represented in this matrix, and then just performs a linear solution of that matrix. And linear things are always much easier and faster than nonlinear things, okay, than iterative solving. So it just, it performs a dot-op simulation first, and then generates a linear matrix, and then just solves that linear matrix, plugging in complex numbers for all of the frequencies of interest. And then it saves a bunch of AC data. Whatever the initial dot-op simulation is discarded, and what is saved is the AC simulation data. Okay. One thing I'll note is that because it is a linear simulation, it does not take into account any nonlinearities. Okay, the nonlinearities are taken into account for the dot-op simulation to find the initial operating point. But for the simulation to find what's the gain as a function of frequency, or what is the input to output ratio as a function of frequency, or whatever, all of that is done assuming that the circuit is linear. And this is basically the same thing as what you've done anytime that you've analyzed a circuit. Say in your microelectronics class, when you analyze what is the gain of this amplifier. Gain in and of itself is a linear concept. It is meaningless when it comes to you know, the second or the third harmonic, or you know, higher powers, higher orders of the Taylor series expansion, right? When you specify what the gain of a circuit is, you're only looking at the first 2 items in the Taylor series expansion. The DC is the first element, and then the first derivative is the second element. Okay, and so what do we have? If I click on this node, what you see is that all that's plotted is a straight line across all frequencies. That's at 0 decibels. It's so close to 0 decibels that it's saying 0 millidecibels, which makes sense. So it's 0 decibels because it has an amplitude of 1. So an amplitude of 1 expressed in decibels, or a ratio of 1, I should say, expressed in decibels, is 0 decibels. And the phase of this is 0 because we have specified it to have 0 phase, or rather we've simply not entered a phase, so it was assumed to have 0 phase. So everything else, when I click anywhere else in the circuit, voltages or currents, those are being plotted with respect to this AC source. So if I click on this node here, what we are observing is 0 decibels, meaning a ratio of 1 at low frequency, which is why it's a low pass filter. And then it peaks a little bit, and then it starts falling at a rate of minus 40 decibels per decade as the frequencies increase, as is typical for any second order low pass filter. And the phase goes from 0 degrees, you can read it off on the right, goes from 0 degrees to minus 180 degrees at high frequencies. Okay. All right, let's do another example of an AC simulation. Let's just go ahead and take our BJT circuit, and I'm going to modify it a little bit. I'm going to change this resistor to a 1K resistor. I'm going to drag this over, so the drag command, and we'll add a capacitor here. We'll add another capacitor here. So what we're doing now is we're adding frequency-dependent components into a circuit that was previously frequency-independent. Because resistors and a BJT without any transit time associated with it, all of these are basically instantaneous. All of whatever happens with them is instantaneous. So meaning that there's no frequency dependence. So I'm just going to add some frequency-dependent components like these capacitors. I'll specify this one to be 1 millifarad and this one to be 5 nanofarads. And this voltage source, I'm going to give it a DC value this time. I'm going to call it 3 volts. And I'm also going to give it an AC voltage. So I'm going to right-click it, hit Advanced. And in AC amplitude, I'll type in 1. Okay, cool. Now, instead of a DC sweep, I'm going to do an AC sweep. Now, maybe I want to do a DC sweep again later. I don't know. So this is what I'll do. I can right-click it, and it'll bring up this menu. If I hit Escape, then it brings up this dialog, which is sort of a power user dialog. Instead of having the graphical user interface, I can just edit the text directly. Now, one of the neat options here is that there's this radio button that says comment. So I'm just going to double click that. And now that DC command statement is now a comment, and it's not going to run that simulation. If I want to run it, I can right click it and click Spice Directive. But I'm not going to because I want to run an AC simulation. Okay, so I've commented out my DC simulation. Well, let's do an AC simulation. So I'll type s.ac. This is going to be a decade sweep, 100 points per decade. We're going to sweep from, say, 2 hertz to 200 kilohertz. Okay, and I'll put that onto the schematic. And let's hit the running man. The waveform window is minimized right now, so we'll bring that up again. Okay, so there's a bunch of stuff going on. I don't know what's going on, so I'll just delete everything. Okay. So here's the voltage source that's coming in. It's at 0 decibels. And this is the output voltage here. So let me just click the output voltage twice. So the output voltage in the mid-band is at about 40 decibels. So that's about a factor of 100, which is a much higher gain than the amplifier that we had previously. And that's because we've added this capacitor so that it's no longer emitter degenerated within this range of frequencies. So now we have a common emitter amplifier within this range of frequencies that's feeding a 1K resistor. At low frequencies, this capacitor begins opening up. As frequency goes up, this capacitor kind of shorts out and it becomes just a common emitter amplifier. And then at very high frequencies, this resistor starts getting shunted out by this capacitor. And so the gain starts falling again. So we can think of this kind of as a bandpass filter of sorts, where we have this range of frequencies that the amplifier operates, and at low frequencies, it doesn't amplify, and at high frequencies, it also doesn't amplify. Okay, now one thing I want you to notice is that even though I set the AC amplitude of this voltage source to 1 volt, the simulation doesn't really care about the fact that this transistor is nonlinear. Remember that for an NPN amplifier that doesn't have any emitter degeneration, the current that runs through that NPN goes up by a factor of 10 for every 60 millivolts. So a 1 volt perturbation would cause tremendous variations in the current that flows through that transistor, and therefore the voltage that comes out the other side. It would be incredibly nonlinear. It would not be, if you fed in a sinusoid of 1 volt amplitude, the output would not be a sinusoid. It would be something very different from a sinusoid. And yet this simulation doesn't really care, and that's because an AC simulation is performed assuming linearity. So any nonlinearities don't matter. All of those nonlinearities only mattered for the dot-op simulation that established the operating point, the quiescent current through the transistor, and the DC voltages, and so forth. Once that's established, then the AC simulation is performed, which assumes linearity of all components. All right. Let's just give a cute little example of another thing that you can do with an AC simulation. I'll just start a new schematic. If I want to measure the impedance of some components, let's say I have a resistor and a capacitor and another resistor. And I create a network with these three components arranged like such. Okay, and I want to measure the impedance of this network. So let's say this is 1 nanofarad, this is 1 meg. I can perform a simulation that will find this impedance because I know that the impedance of a network tells me the ratio between the voltage and the current. Specifically, the voltage across a network is equal to the impedance of the network times the current that runs through it. So if I create a current source, I'll just rotate it like that. If I create a current source to feed that network, and I simply set that current source's amplitude to 1, then the voltage across this network will be equal to its impedance, just with different units. The units will be volts instead of ohms. So let's see that. I'll type S for SPICE command, .AC, decade, 100 points per decade, from 1 hertz to 10 megahertz. Okay, we'll hit the running man. And here we go. I click this, and that is the impedance. Oops. Okay. So all I did is I have an AC amplitude of 1, and I clicked the voltage of this node, and we see the impedance of this network. It is being expressed as a voltage, but because the amplitude of the AC current source is simply 1, the voltage is simply equal to the impedance with different units. And so what we see is 120 decibels at low frequency. 120 decibels is 6 factors of 10. In other words, 1 million, which is the impedance of this resistor R2, which is what you expect, right? At low frequency, this capacitor opens up, so this network is irrelevant, and we have 1 mega ohm of impedance at low frequency. And then at some sufficiently high frequency, this capacitor begins dropping its impedance. So then we see the impedance of that capacitor. And then at really high frequencies, this resistor becomes a higher impedance than this capacitor. So at high frequencies, we have 3 factors of 10, 60 decibels. I could, if I wish, right-click on the vertical axis, and instead of plotting in decibels, just plot logarithmic. Hit OK. Now it shows the number instead of the decibels. So at the top, we have 1 million, and at the bottom here, we have 1,000 ohms. Okay. All right, let's talk about transient simulations. So I'm going to take, was it this one? Yeah, this schematic right here. And instead of running an AC simulation on it, I'm going to run a transient simulation. How do you run a transient simulation? Well, I'm going to right-click on the simulation command. And instead of AC analysis, I'm going to click transient analysis. Okay, stop time, let's type 30 microseconds. Time to start, if I don't type anything, it's just going to be default, which is at the beginning. Maximum time step, I usually just don't punch in anything else here. I just leave it like that as much as possible. Okay, now if all I do is run a transient simulation, nothing is actually going to happen. Let's look at the waveform. So let's look at this node here. It's just flat at 1 volt. Why is that? There's this voltage source, but hey, its value is simply 1 volt. You might say, hey, it has an AC value, but that AC value only applies to AC simulations, not to DC simulations, not to op simulations, and not to transient simulations. So I need some sort of a stimulus, something that is time, that changes with time in this circuit in order to observe anything happening. Okay, so I'm just going to take V1 and change it into something that is a function of time. So I right-click on that voltage source, and if I didn't already have an AC amplitude, then it would have brought me to that really simple dialog, and I would have had to press advanced. But since I have this advanced dialog, I can go ahead and click, I can click pulse, I can click sinusoid, which allows me to select an amplitude and a frequency and so forth. I'm going to do a PWL, which stands for piecewise linear. Piecewise linear means you type in a time and you type in a value. And then you type in the next time point, let's say 1 nanosecond. And then you type in a value, 1 volt. And what it will do is it will linearly interpolate between those values. And outside of any values that you've typed in, it will just remain constant. Let's watch that. So piecewise linear, at 0 time, its value is 0. And at 1 nanosecond time, its value is 1. Let's hit the running man. I'm going to click this node right here. So the voltage at node 001, which is the top of this voltage source, if I zoom way, way in, you can see that its value starts at 0 time, and at 1 nanosecond time, it comes up to 1 volt. By the way, here's something cool that you can do, a neat trick that you can do. If you ever want to measure something and measure it quickly without bringing up cursors, you can drag this, the magnifying glass as if you were going to zoom in on the waveform. And if you look at the bottom left of the screen, if you look at the status bar, it shows you the dx, the delta x between the left portion of this little drag box and the right portion of the little drag box, and the dy, as well as the slope. So you can perform really quick little measurements without having to bring up cursors and close the knot every time. That's a neat little trick. I use it all the time. And if you want to escape from that, you just right click. So that way you don't actually zoom in. Okay, now let's go, let's zoom to fit. I actually set it so that if I hit the space bar, it zooms to fit. Okay, so it's just a really fast rise time step. Okay, that's the voltage that's being applied at this end of the network. Now the output of the network might be this node. And as you can see, this network's step response looks like this. This is pretty typical for a second order low pass filter step response. So how does this simulation work? Well, the first thing that happens is it runs a .op simulation. Notice a theme, just about all simulations start with a .op to find the initial operating point of every component. And then once that initial condition is found, then a transient analysis begins. In a transient analysis, another numerical technique called numerical integration is employed to solve for the values of all of the voltages and all of the currents at a particular time point, and then use those as a starting point, having established what the values and what their derivatives are, and then estimating what the next time point is based estimating what those values are at the next time point, and computing something called a relative truncation error in order to figure out if that time step was too large. If the time step was too large and the truncation error was too large, then it decreases as a time step and selects a smaller time step so that it gets a better, more accurate estimate of the value at that time point. And a numerical integration technique such as trapezoidal integration is used to basically make it so that something that runs in with discrete time points, like a computer, like a digital computer, can accurately estimate the behavior of a continuous time differential equation. Okay. And you might ask, what's the accuracy of this? Well, it's kind of hard to tell. It's kind of hard to tell, with a degree of certainty to exactly what the accuracy is. But generally speaking, the accuracy is better than what you typically might care about when you build, because at the end of the day, you're actually going to build a circuit, and the tolerances of all of the components within that circuit are going to introduce substantially more error than the numerical integration technique did. Okay, cool. And you can click around for all of the other node voltages and all of the component currents and so forth. Okay. Now, let's just run another example. So this is, yep, that's our BJT circuit. So I'm going to go ahead and take this BJT circuit, and instead of an AC simulation, I'm going to, by the way, if you control right click on something, then it always brings up the advanced dialog. So I control right click on it and then commented it out. And now I'm going to run a transient simulation. So I'll hit S, type .tran 5 milli for 5 milliseconds, place it on the schematic. And for our source, I'm going to right click it. And this time I'm going to make it a sinusoid. And we'll make it have an offset voltage of 3 volts, 10 millivolt amplitude. And it's going to be a 1 kilohertz sinusoid. Hit OK. So you'll notice that for a transient simulation, what's actually being run for this voltage source, it's not this AC1 command. That's completely ignored during a transient simulation. it's the specification that it's a sinusoid with a 3-volt offset, 10 millivolt amplitude, and 1 kilohertz frequency. So let's hit the running man and see what happens. Here we go. All right, cool. That's voltage at node 002. What's node 002? This voltage here. Okay. By the way, here's something that you can do. So I haven't labeled any nodes, which has been kind of annoying because I don't know what anything's called. And I just let LT-Spice automatically select names for me, which is not always the best. It's nice when you want to just get started, draw your schematic and get it running really quickly. But at some point when you're probing around and trying to figure out how your circuit works or why it's not working, it becomes necessary to start naming things. So there's a hotkey, it's F4. In my case, I've changed the hotkey to N for name. And when you bring up this dialog, it allows you to type in the name for a node. So I'll type in, let's say in for the input node. And then we'll do another one, out, for the output node. And I'll click on that node to add it and right click to escape. Okay, so now these nodes are named. But remember, the fact that I modified the schematic, the fact that I added these names, has changed the netlist. If I view the netlist, I'm going to see some lines in here that show out, the node that's named out, and the node that's named in, right? These are part of the netlist specification. But it hasn't rerun the simulation yet. So whatever simulation, whatever waveform data is here is totally bogus. If I like click add traces, there's nothing in here that says in or out because this waveform data is representative of whatever I simulated last time. So the fact that I changed the schematic means I need to rerun the simulation. Okay, now node 002, I have no idea what node that is. It's definitely not what it used to be. This is 1, so this is node 002. If I want to click the output, I'll just click on that, and hey, look, it's plotting voltage of node out. Okay, cool. So we've got this nice cool waveform, and it's a transient simulation, and we're seeing the actual value in volts, not decibels, nothing abstract. And also, if you look kind of closely, you can kind of see that there's a little bit of nonlinearity going on. This doesn't look like a perfect sinusoid. It's a little bit more rounded at the top and a little bit sharper at the bottom. Okay, so a transient simulation, it's using the iterative numerical solver that the .op simulation uses in order to be able to solve for the device equations of nonlinear device components, and is using a numerical integration technique to find the way that values evolve over time. So if you really want to observe the behavior of a circuit in the presence of nonlinearities, then you really want to run a transient simulation or a .dc simulation if you don't care about its transient response. Okay, so transient simulations show component nonlinearities. Basically, transient simulations allow you to simulate, to solve nonlinear differential equations, sets of nonlinear differential equations. Okay. All right. We can also measure distortion. So distortion refers to the fact that when you build a circuit using nonlinear components, when you build an amplifier, let's say, using nonlinear components, and you feed in a sinusoid, what comes out the other side is not just a sinusoid at that one frequency, but it is now a superposition of a sinusoid at that frequency, as well as sinusoids at harmonics of that frequency, at multiples of that frequency. In order to observe that, we can use the .4 command. So I'll just hit S, type S for a spice command, .4, and we'll say 1K V out. Okay, and we'll add a few more spice commands. You don't really have to know these at the moment, but .options plot when size equals 0. And we will change the transient simulation to run from from 990 milliseconds to 1 second. Basically what that means is that it's going to simulate the circuit but it's only going to begin saving data after simulating the first 990 milliseconds and stop the simulation at 1 second. Okay, so let's just have a look. So this doesn't look too different from what it used to look like, but there is a slight difference. There was this weird little startup transient that was present at the beginning, at the beginning of the simulation. Because we've let it settle for close to a second of simulation time, that startup transient is gone. Okay, so anytime that you want to do like a distortion analysis or an FFT or something like that, you want any initial startup transients to be settled out, and then you want to run the remainder, the saved portion of the simulation, for an integer number of cycles. Okay, cool. So where's the distortion analysis? We added this .4 command to view the distortion analysis. Well, in order to see that, you have to go to View Spice Error Log, or you can hit Control L. So if I view the error log, it shows me this. It shows me a bunch of stuff. It shows me like how the simulator did. It said it used modified trapezoid for the transient simulation, a bunch of other things, and it's telling me that harmonic number 1 has this component of voltage. Harmonic number 2 has that. Harmonic number 3, and so forth. And it normalizes them, and then it also computes what is the total harmonic distortion. For this circuit, with this amplitude, the total harmonic distortion is 9.2%. Okay, cool. Here's another neat trick that you can do with transient simulations. So I showed how you could measure the impedance of a component using of a network using an AC simulation. Here I'm going to show you how to measure the capacitance of a capacitor using a transient simulation. And you might ask, well, why do I care to measure the capacitance of a capacitor? Well, what if you don't have a capacitor that is a constant valued capacitor? Let me show you what I'm talking about. So I'm just going to set this capacitor's value to 1 nanofarad. And I'll set this voltage source. I'm going to set it to I'll hit advanced, a PWL that goes from 0 volts at 0 time to, at 10 nanoseconds later, 10 volts. So it has a rise time of 1 volt per nanosecond. Okay, now let's just run a transient simulation. Control E for mirror. I'll run a transient simulation, s.tran for 10 nanoseconds. And then let's see what happens. Hit the running man. And if I plot the current that flows into that capacitor, I see 1 amp. Why? Well, this voltage that is being applied by this voltage source goes from 0 volts to 10 volts in 10 nanoseconds. So it has a rise time of 1 volt per nanosecond. Now, if I have a voltage, a dVdt of 1 volt per nanosecond, and apply it across a capacitor whose value is 1 nanofarad, then it will have 1 amp of current flowing through it. Okay, so the current that flows through the capacitor is directly proportional to how many nanofarads it has. Let's say I hit 2 nanofarads. Right now it says 2 amps. Okay, and the fact that it's constant is reflective of the fact that it is a constant valued capacitor. Now I can add a non-constant capacitor by, let's say, a diode. You can also specify nonlinear capacitors using using equations if you want to. You can look at the help file for that if you want to know more. So here's a diode, and diodes are generally speaking not constant valued capacitors. We often call those nonlinear capacitors. Now I need to add a model for this diode, so I'm going to just add a model statement, .model DD. Basically, I'm leaving the name of this diode the same, that it was D, and I'm creating a model that's named D, and it is a diode. And I'm going to set it to a saturation current of 1 femtoamp and a zero bias capacitance of 1 nanofarad. Okay, all right, let's hit the running man. If we observe the current through this capacitor, it's exactly the same as it was. If I observe the current flowing through this diode, well, it's negative because it wants, the default is to measure the current flowing from anode to cathode. I can get around that actually. Watch this. Well, for one, I can either right-click on the name of it and then type in a minus sign to plot the negative of its value. Or if I hover over this wire and hold down Alt then it allows me to plot the current flowing through that wire. That's a neat trick. Okay, so you can see that the current that flows through this diode starts at 1 amp, meaning that it starts at 1 nanofarad capacitance. And then the current drops, meaning that its capacitance is also dropping. So that's just a neat little trick. You can use transient analyses to measure the capacitance of a component that does not have a constant capacitance with voltage. And if I want to change the x-axis, let's say, this voltage is named node 001. So I can right-click on this axis. Instead of time, I can put voltage of node N001. And now these quantities, this current is being plotted as a function of the voltage instead of time. Right, so now we are seeing the capacitance value as a function of voltage. Okay. So let's see what other skills that we want to cover when it comes to plotting stuff. We've shown how to plot node voltages and currents, and we've also shown how to delete traces. Plotting voltages across nodes. That's a neat little trick. What's a good circuit to show that on? Here's a good one. Okay, so let's look at this circuit right here, draft 7. Let's suppose that I want to measure the voltage across this transistor from its collector to its emitter. So that's called VCE. If I want to measure this transistor's VCE. Now, one way that I could do that is I could say, okay, this voltage here is named V out, and this voltage here is named VN002. So I can right-click this. I can right-click this trace and say V out minus VN002. Okay, that's the voltage VCE across that transistor. Okay. Now there's another neat little way that you could do it, and it's this. When you hover over a node, it turns into a probe. If all you do is click it, then you measure that voltage with respect to ground. But if you click and drag, then you get a second probe. And when it turns black, that shows that you are probing the voltage from this node to that node. So now when you release, that shows the voltage between those two nodes. And it has special syntax. V out comma N002 means the difference in voltage between node out and node N002. Okay, so that's how you measure the voltage across nodes. And as I showed previously, you can also measure the current through wires. Now, as for, there's another neat thing that you can do. You can plot the power dissipation of a component. So after running a simulation, if you hover your mouse over a component and hit the Alt key, then your mouse turns into a thermometer. And when you click on that component, it generates a waveform where the expression is whatever is necessary to show the power being dissipated by that component. Okay, so it's taking the node voltages and the terminal currents that are that component is connected to, and performing the math to show you how much power is being dissipated by that component. And I can do that for everything. I can show how much power is being dissipated by this voltage source, by that voltage source, and so forth. What you'll notice is that any real component, like this transistor, it dissipates a positive amount of power, on average about 12 milliwatts here. If I do the same thing for this voltage source, I get a negative value. And that's indicative of the fact that voltage source V2 is supplying power instead. So the power being dissipated by it is a negative value. Okay, I've already shown how you can do some waveform math. Zooming, you do just by clicking and dragging. You can auto scale, you can zoom to fit. Another thing that you can do is auto scale the y-axis. So let's just say that we've decided that, what's a good example? Let's suppose that I've zoomed in and and I want to, I feel like I have the x-axis correct. I don't want to zoom out all the way on the x-axis, but I just want to fix my y-axis so that I can see the input voltage here. I can auto-range just the y-axis, okay? And I do that so much that I specified a hotkey for it. I type y, and that auto-ranges the y-axis. And for me, space is auto-scale everything. Okay, we already showed how to do these measurements, adding traces, adding plot panes, performing FFT. So let's look at the output voltage for a moment. Oops. So let's look at the output voltage. Okay, now if I right click somewhere and I go over view, I can view the FFT. I can select V out to view the Fourier transform of the output voltage. And there's a bunch of other neat little options for how it's going to be windowed and filtered and so forth. Click OK. And this is the Fourier transform of the output voltage. Now it goes out to really high frequencies because this is a pretty short time simulation. So I'm just going to set the maximum frequency to say, 20 kilohertz, okay, which is the upper bound of human hearing. And maybe I'll set it to a linear scale instead. Okay, so here's 1 kilohertz, the component of this output voltage at 1 kilohertz, the component at 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6, and so forth. And when we performed this Fourier analysis with the .4 statement, that showed the first 10 harmonics, or the fundamental and the 9 harmonics after it. Okay, and you can do all sorts of neat stuff with FFTs and all sorts of stuff like that. Okay, all right. Let's talk. I'm definitely not going to cover everything that I wanted to cover today, but that's fine. Let's just go through some of the. I'm going to stop before talking about the role of simulation, or maybe I'll just cover a tiny bit of it. But yeah, let's just pump through this. So if I create a new schematic, I've shown you how to make resistors, capacitors, inductors, right? R, C, L, those are the hotkeys for those. And to add a voltage source or a current source, then you have to use the add dialog and type in voltage source or current source, right? So those are the components that we've dealt with so far, and as well as diodes and transistors. Now there's a few other components. We have the E, F, G, and H. So E is a voltage-dependent voltage source. So it has 2 sense terminals and 2 output terminals. So it measures the voltage across something, like let's say you want the voltage across this resistor to be scaled up by this voltage source. You might set this voltage source's value to be, say, 1, and for every volt across this resistor, the voltage between these 2 terminals is going to be 1 volt. I could set it to a different value. I could set it to 2 volts or something like that, or 2 volts per volt. But anyway, E is a voltage-dependent voltage source. G is a voltage-dependent current source. So it measures the voltage across something. It doesn't necessarily have to be across just a single component. It could be from one node to another node, arbitrary nodes. And it generates a current in proportion to that voltage. And the amount of current is specified by its value. Let's say 1 milli for 1 milliamp per volt. That would be its transconductance. Okay, and then we have F. This is a current-dependent current source. And we also have H, which is a current-dependent voltage source. Now, one thing that you'll notice about these current-dependent components is that they don't have any terminals. Because, well, that wouldn't be meaningful. You can't measure the current across something. And at least there's no good way of drawing the fact that you want to measure the current through a component. So the way that these components work is where it says value, you have to type in a component and specifically a voltage source. So let's call it V sense 1. Which means that in my circuit, I would need a voltage source. And I would call this, I would set its value to 0 probably. And I would call it V-sense. And within my circuit, this component would sense the current that flows through something. I don't know, maybe you have like a bunch of, some resistors in a circuit or something like that, right? You've built up a circuit like this. And you would like this current-dependent current source to have its value depend on the current that flows from left to right here. So you would do it something like this, okay? So now this current-dependent current source would have a current in proportion, and specifically in direct proportion, to the current that flows through this voltage source. That's just, this voltage source, all it's being used for is to sense the current that flows. Okay, so for a current-dependent current source and for a current-dependent voltage source, you need to have a sense voltage source, a voltage source that senses the current somewhere for them to mimic. Okay, cool. How do you create transformers? Well, if I want to create a transformer, I'll drop in an inductor, and then I'll drop in another inductor, and maybe I'll give one a value 1 millihenry, 9 millihenry, oops, 9 millihenry. And in order to make it into a transformer, I have to set a coupling coefficient. So I'll add a spice command, S, K1, L2, L3. It doesn't have to be 1. It could just be 2, or it could be 3, or it could be nothing. And I'll set it to 1. Okay. Now these dots show up on these inductors, indicating that they are now coupled. And it indicates what the orientation of that coupling is. Okay. So what does that mean? It means that these two inductors are now coupled with a unity coupling coefficient. Imperfect transformers don't have unity coupling coefficient. They're typically, say, 0.995 or something like that. But anyway, you can set that coupling coefficient, and now these two inductors are coupled as a transformer. And the turns ratio of this transformer is 1 to 3. Okay, because the inductance scales with the turns squared. Okay. All right, so that's how you make a transformer. We've shown how you add a diode. Just hit D for a diode. If you want an NPN, use the add dialog, type in NPN. If you want a PNP, add dialog, PNP, and rotate, rotate. It always instantiates upside down. For NMOS, add dialog, NMOS. And for PMOS, PMOS. And it always comes in upside down, so rotate, rotate for the PMOS. Okay, so these are all your nice, good old nonlinear components that you learn about in microelectronics. You can also add an ideal switch. Now, it's not perfectly ideal, but it's a voltage-controlled switch which measures the voltage across two nodes, and depending on that voltage, closes a switch. And like diodes and NPNs and NMOSs and stuff, you would have to add a model. So you could say dot model switch, and it might be on resistance of 1 milliohm, 1 gigaohm off resistance, a threshold voltage of 0.5 volts, something like that, right? So that's how you add a switch. You can also add transmission lines. So this would be a transmission line with a 50 nanosecond propagation delay through it and a 50 ohm characteristic impedance. If you want this transmission line to be representative of, say, a coax cable that you might find in lab, typically the coax cables that you find in lab are 50 ohm characteristic impedance transmission lines that are about 1 meter long. And a 1 meter long transmission line that uses Teflon as its dielectric will have a propagation delay of 5 nanoseconds. Okay, so now this transmission line is representative of a 1 meter long coax cable that you might put on your oscilloscope. You can also add ideal logic gates. So we can go here and go to digital. And you can have AND gates and buffers and inverters. So this allows you to sort of build up a behavioral digital circuit. Okay. And also there's a bunch of built-in models for actual components. So say, for example, for an op amp, we have a bunch of op amps here. And you can just, like the 808040 made by Analog Devices, you just click that and add it to the schematic. You have to power it and stuff, but once you hook it up correctly, then it'll run. Okay, and I think that's what I want to talk about there. Okay. Yeah, let's show this one for, do I want to? Now I'll skip this one. I'll skip this one. I'll leave this one up to you guys to simulate. Okay, let's do a noise simulation real quick. So is it this? Yes. Okay. All right. So another simulation type is the noise simulation. Now, I'll mention the noise simulation is probably not one that you're going to encounter unless you do graduate studies or unless you're professionally employed. But I'll show it to you anyway, just because it can be insightful. Okay, so now I'm going to do a noise simulation. So I'll do .noise. Now, I always forget what the parameters are, so I'll just put it on the schematic and then right-click it. Okay, so the output of this circuit, is this node labeled out. So output is voltage of out, and the input to the circuit is V1. Okay, type of sweep, we'll just do decade. Number of points per decade, 100. Start frequency, let's do 20 hertz to 20 kilohertz. So you'll notice that this is looking very much like an AC simulation, and that's because it is a type of AC simulation. But watch what happens. When I click on the output, instead of showing me the gain of the circuit in decibels, it shows me this weird stuff. 22 nanovolt per root to the power of 1/2. Sorry, per hertz to the power of 1/2. 27 nanovolts per hertz to the power of 1/2. We often call that nanovolts per root hertz. And so what that's actually specifying is noise density. Okay, that's a concept that you'll run into at some point when you talk about noise analysis and so forth. Noise density. How much noise do you get per hertz of bandwidth, or per square root of hertz of bandwidth? And as you integrate over a wider bandwidth, then you get more noise. Okay, how do I know? Okay, so this is the noise density, but what is the actual noise in microvolts? Because that's something that you might care about more, because that dictates the signal to noise ratio. You know, if your signal is 1 microvolt RMS and your noise is 1 microvolt RMS, then your signal to noise ratio is unity. Okay, so what is the RMS noise? Well, if I control click on this, on the waveform name, then it integrates over this bandwidth, and it shows me what the RMS noise is across this bandwidth. From a range of 20 hertz to 20 kilohertz, it's 3.6 microvolts. Okay. Now, in fact, that behavior of integrating across a simulation is not specific to noise simulations, but it also happens for other simulations. I'll show that in a second. Now, another interesting aspect of these noise simulations is that if I click on a different component, like say this resistor or this transistor, what it shows me is the noise contribution of that component to the output noise. Okay, so if I click on this resistor, it shows me 4 nanovolts per root hertz, which is the noise contribution of a 1 kilo ohm resistor. If I click on the transistor, it's showing me 26 nanovolts per root hertz, which is most of the output noise. So this transistor is contributing most of the noise of this circuit. Okay, now to demonstrate, let me just comment out the noise simulation again, and I'll bring up the transient simulation. Okay, and then rerun it. Okay, so that point I was talking about integrating a waveform, if I control click on this waveform name, then it integrates across this entire, whatever's currently viewed in the window, and it shows me the average across that time, the RMS during that time. If I say plot the power dissipated by this component, and then I control click on it, then it shows me the average power as well as the total power dissipated during this window of time. So during this 10 millisecond window, it dissipated 120 microjoules. Okay. All right, so some final notes about how to get simulations working. Every circuit must have a ground. You'll notice that I always added a ground to the circuits. Every circuit must have a ground because it serves as the 0 voltage reference. Floating circuits that are decoupled from ground are not allowed because their voltage is undefined, right? All of the voltages within a circuit are computed with respect to ground by a simulator. Now, when specifying components, it turns out that their values and their labels are case insensitive. This is a standard among SPICE, among LT SPICE, P SPICE, or any other SPICE. It's case insensitive. So say, for example, this 5 nanofarad capacitor, if I made it a 5 big N capacitor, oh, I guess it automatically changed it for me. It didn't really, let's say this 1K resistor, if I do a capital K, right, it doesn't change the fact that it's 1K. So one thing that you might wonder is, how do you specify, let's say, a 1 mega ohm resistor instead of a 1 milliohm resistor? Well, the way that works is you have to type out meg. So that's a 1 meg resistor, and this is a 1 milliohm resistor. Okay. If you add a resistor and call it 1 capital M, it's actually smart enough now to just lowercase it for you so you don't get confused. So if you just try capital M, it's not going to make it a 1 mega ohm resistor. It's just 1 milliohm, because LT-Spice is case insensitive. And as a result of being case insensitive, the only way to specify meg as separate from milli is to type it out as more than one character. When it comes to units, like let's say millifarad, I could type milli F, nano F if I want. I could type 10 volts if I want, but it's not really necessary. It's not needed because LT-Spice already knows what units that component should be using. And in addition, it's actually a little bit scary, because what if I wanted to make a 1 farad capacitor? If I type 1 capital F, it actually gets, because it's not case sensitive, it gets interpreted as 1 femtofarad, which is 15 powers of 10 too small to be a 1 farad capacitor. So generally speaking, when you're simulating, don't type the units. It's just usually not a good idea to type the units. The units are going to be there anyway. Okay. Okay. So here's an example. If you want a 9 meg resistor and a 1 meg resistor, so this would be like a 10-to-1 divider, you type it out, mega ohms. And a 1 femtofarad capacitor is like so. Okay. All right. I'm going to stop it here. If you guys want, I can come back for another talk to go over the rest of the material that I've presented. Mostly it covers where simulation falls within the design flow, within the life of an electrical engineer, how you use it. So like what we've demonstrated right now is the technical aspects of using it, right? Sort of the procedures. But there's more to discuss when it comes to why you use a simulator, under what circumstances you use a simulator, as well as what some of the gotchas are, and so forth. So if you guys want, I can come back and do another video about, or another webinar for that as well. But I'm going to call it for this one. Okay. Does anybody have any questions?
More of a comment, but thank you so much. Wow, so much information. I really appreciate you coming here and showing us all this amazing simulation.
No worries. I'm excited to do it.
Yeah, and I would say I would love to get to go through some of the role of simulation and where in the design flow that plays, or how it falls into it. So yeah, that would be much appreciated.
All right, sounds good. So let's set something up at some point. Just let me know. Not later tonight.
Oh, hey, I do have a really simple question.
Yeah.
How do you do those thick lines?
Oh, for the waveforms?
Yes, no doubt.
So if you go to control panel, where it says waveforms, there's data trace width.
Thank you so much. That's really improves the readability of some of these designs.
No worries.
Can you guys hear me? Sorry.
Yes.
Awesome. So thank you, Zeke, for hosting the webinar. Like I learned so much, like so much more than what I've learned in my classes. Like anytime I will review the recordings just to kind of see everything I went through. And yes, I will, like, you covered so much and you helped us learn so much in LT Spies that we didn't know about. We would love to have you again for another webinar. If it's all right, I would love to send you an email later tonight or tomorrow morning to follow up to set up another part 2, I guess, for the LT Spies webinar. Would that be all right?
Yeah, absolutely.
Awesome. Thank you, Zeke.
All right.
Yep.
One last question. Are you, I know that you teach a power electronics course on campus. Are you doing that in the spring?
I haven't established that yet.
Okay.
So
Right.
I guess we'll find out.
Right on. Okay, I'll keep an eye out for it.
And with
Okay.
that,
That's it. I wish you guys a good night. Thanks for having me.
All
Have a
right.
great
Thank
night.
you.
Thank you.
Zeke.
Okay, good night.